Assalamu alaikum students, very good morning. So we are continuing with our lecture series by the Department of Mathematics, the New College, Chennai. So today we are going to see about problems based on Cayley-Hamilton theorem. This particular problem is in the curriculum of B.Sc. Mathematics, B.Sc. Computer Science, B.Sc. IT, B.C.A, M.C.A and etc. So this will be very useful, so kindly watch it carefully. So we are going to talk about Cayley-Hamilton theorem. First we have to understand what is the actual statement of it. Every square matrix satisfies its own characteristic equation. So we know what is a square matrix, wherein the number of rows and number of columns are equal, so that we call as a square matrix. And the characteristic equation we obtain using this method. This is actually by taking the determinant of the matrix minus lambda times I and equating it to 0, we get the characteristic equation. So the word satisfies means we have to, this determinant value will give you an equation on lambda. So we have to replace that lambda with the given matrix and we have to prove that the RHS becomes a null matrix or all zero matrix. So that is what we are going to do. The actual working rule is first we have to find out the characteristic equation by taking the determinant of A minus lambda I is equal to 0. And substitute lambda with the matrix A and check if it is satisfying the characteristic equation. That way we can actually verify the Cayley-Hamilton theorem, and hence if they ask us to find the A inverse value after verifying Cayley-Hamilton theorem, we have to pre-multiply A inverse and solve for A inverse. That is the general working rule for this problem. So the given question is, verify Cayley-Hamilton theorem for the matrix A is equal to 1, 1, 1, 1, 2, minus 3, 2, minus 1, 3, and after verifying by that equation we have to find out the value of A inverse. So the first step, as you all know, is to find the characteristic equation. For that what you have to do, we have to equate the determinant of A minus lambda I to 0. So given function, given matrix is a 3 cross 3 matrix. So our identity matrix is going to be 1 0 0 0 1 0 0 0 1. It is also going to be an 3 cross 3 matrix. So we are going to multiply that with lambda, a scalar. That means we get lambda 0 0 0 lambda 0 0 0 lambda. So we are subtracting that matrix from the given matrix A. So we all know that lambda I has values only in the diagonal elements. So we'll actually subtract from the first element, that is 1 minus lambda. The other two entries will be 1 and 1. The second row will be 1, 2 minus lambda, minus 3, 2, minus 1, 3 minus lambda. That is how this A minus lambda I matrix is going to be. For that we have to take the determinant. So this is nothing but determinant value of 1 minus lambda, 1, 1, 1, 2 minus lambda, minus 3, 2, minus 1, 3 minus lambda. We have to equate this to 0. So there is a easy method to find this out. We all know that this is a 3 cross 3 matrix and our characteristic equation is going to be a cubic equation. So the general equation that we consider is, let the characteristic equation be lambda cube minus s1 lambda plus s2 lambda, s1 lambda square plus s2 lambda minus s3 is equal to 0. Lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0, wherein s1 is the sum of all diagonal elements of the matrix. Sum of all diagonal elements. S2 is the sum of the minors of diagonal elements. And S3 will be determinant of the given matrix A. So with this idea, let us understand what is S1. So we have to get the value of S1, S2 and S3 from the given matrix A. So S1 is equal to addition of the diagonal elements. So sum of the diagonal elements, 1 plus 2 plus 3. So that is 1 plus 2 plus 3, which is equal to 6. Likewise, S2 is the sum of the minors of the diagonal elements. So what do we have here is, for the element 1, the minors are, we have to leave off the first row and first column. So the minors are going to be 2, minus 3, minus 1, 3. So they are 2, minus 3, minus 1, 3. Plus the minors of the second diagonal element, that is 2. So we have to leave off the second row and second column. That way we get the minus to be 1, 1, 2, 3. 1, 1, 2, 3. Plus, for the third diagonal element, we have to find the minors. So we have to leave off the third row and third column. So we get 1, 1, 1, 2. So this can be written as 3 into 2, that is 6 minus, by formula we have a minus. So here we have minus 1 into 3. So the minus 1 into minus 3. So it is going to be positive 3. By formula we have a negative. So it is going to be 6 minus 3 plus 3 minus 2 plus 2 minus 1. Just cross multiplied and added negative sign in between. So this value is equal to 3 plus 1 plus 1, which is equal to 5. So our S2 value is equal to 5. So S3 is equal to determinant of A. So let me get the A matrix first. 1, 1, 1, 1, 1, 1, 1, 2, minus 3, 1, 2, minus 3, 2, minus 1, 3, 2, minus 1, 3. So to find the determinant, we all know what you have to do is, you have to take the minors of the first element. So 1 into 3 into 2, 6 minus 1 into minus 3 is plus 3. So 3. The next thing is we have to go with the next element in the first row, that is the second element in the first row. We start with negative of that element along with its minors. So it is 3 into 1, 3, minus of minus, so it is plus 6, plus 1 into, for this element we have to find the minors, so it is going to be minus 1 minus 4. I hope you all get this. So this is equal to 1 into 3 minus 1 into 9 plus 1 into minus 5. So the values are 3 minus 9 minus 5. So these two clubs to get minus 14 plus 3. So that is minus 11. So the given matrix, we have got S1 value, S2 value and S3 value. Now the actual, therefore the characteristic equation is lambda cube minus S1 lambda square. So our S1 value is actually, S1 value is 6 minus 6 lambda square. Our S2 value is plus 5 lambda and our S3 value is minus 11. There we have minus S3, so it is minus of minus, plus 11 is equal to 0. So this is our characteristic equation. Lambda cube minus 6 lambda square plus 5 lambda plus 11 is equal to 0. Now we have to solve. Now we have got the actual characteristic equation. The next step is we have to verify Cayley-Hamilton theorem. So what you have to do is, at the place of lambda, we have to replace the exact matrix itself. So what you have to verify is A cube minus 6 into A square plus 5 into A plus 11 into, here it is a number, it's a constant number, but here we are dealing with matrices. So if you have to change the scalar into a scalar matrix, so we have to multiply that with identity is equal to 0. This is what we have to prove. So A cube minus 6A square plus 5A plus 11I should be equal to 0. For this, what do we need? We know A, we know I. So we need A square and we need A cube. So we need A square and A cube. Finding A square and A cube and then substituting here, we have to prove that it's going to be a null matrix. So that is the next step. So the first step is to find A square, which is equal to A times A. So the actual matrix A is 1, 1, 1, 1, 2, minus 3, 2, minus 1, 3. So same matrix is here, 1, 1, 1, 1, 2, minus 3, 2, minus 1. So now we have to multiply this matrix with this matrix. So this we do by going term by term. So first row we have to multiply with first column element of the next matrix. So second row with first column, third row with first column. That will give you the first row elements of A square. So A square is equal to, let me have a big matrix here. So 1 times 1 is 1. Again 1 times this 1 is again 1. So I have to add 1. So 1 times 2 is 2. So this is going to be your first element. Likewise, first row with second column will be this element. So 1 times 1 is 1. 1 times 2 is 2. 1 times minus 1 is minus 1. That is your second element. For the third element, in the first row of A square, we have to multiply the first row with third column. So 1 times 1 is 1. 1 times minus 3 is minus 3. 1 times plus 3 is plus 3. Likewise, to get the second row elements, we have to multiply the second row with first column, second row with second column, second row with third column. So it's going to be 1 times 1 is 1 and 2 times 1 is 2 minus 3 times 2 is minus 6. 1 times 1 is 1, 2 times 2 is 4, minus 3 times minus 1 is plus 3. 1 times 1 is 1, 2 times minus 3 is minus 6, minus 3 times 3 is minus 9. Likewise, for the third row, you have to multiply third row with first column. So that is 2 times 1. So you get 2. Minus 1 times 1 is minus 1. 3 times 2 is 6. So 2 times 1 is 2. Minus 2 times 2 is, minus 1 times 2 is minus 2. 3 times minus 1 is minus 3. Likewise, 2 times 1 is 2. Minus 1 times minus 3 is plus 3. 3 times 3 is 9. So if you add these individual terms, you get the exact elements of A square. So that is going to be 1 plus 1 plus 2, that is 4. So 1 plus 2 minus 1, that is plus 2. 1 minus 3 plus 3 is 1. So we have the first row elements to be 4, 2, 1. And the next two elements are 1 plus 2 is 3, minus 6 means it is going to be minus 3. And 1 plus 4 plus 3, 4 plus 4, that is 8. 1 minus 6 is minus 5, minus 5 minus 9 is minus 14. The next one is 2 minus 1, that is 1, plus 6 is 7. 2 minus 2 is 0, minus 3, so minus 3. 3 plus 2 is 5, plus 9 is plus 14. So the actual A square is 4, 2, 1, minus 3, 8, minus 14, 7, minus 3, 14. So for AQ, we have to multiply this matrix A square that we have obtained now with the given matrix A. So that is our next step. So to find AQ, which is nothing but A square times A is equal to let me take the two matrices along. So A square is 4, 2, 1, minus 3, 8, minus 14, 7, minus 3, 14. And the A matrix is 1, 1, 1, 1, 2, minus 3, 2, minus 1, 3. So now we have to find the value of A cube by multiplying these two. The same method as we used for the A square. So we have to go first row with first column, first row with second column, first row with third column. So this time I am directly going to write what is A cube. So just follow along with me. It is going to be 4 times 1, that is 4, plus 2 times 1, it is 2, plus 2 times 1. So 4 plus 2 plus 2, that is going to be 8. Likewise, first row with second column. 4 times 1 is 4, 2 times 2 is again 4, 1 times minus 1. So 4 plus 4 minus 1. So that is going to be 4 plus 4, 8, minus 1 is 7. First row with third column. 4 times 1 is 4, 2 times minus 3 is minus 6, 1 times 3 is 3. So minus 6 plus 3. So it is minus 3. 4 times 1 is 4. So 4 minus 3 is going to be 1. So the first row is over. Likewise for the second row, minus 3 plus 8 minus 28. So the value is minus 23. Likewise, minus 3 plus 16 plus 14, the value is plus 27. Next row is minus 3, minus 24 and minus 14 3s are 12, 42. So the value is, by adding we get negative 69. Likewise, for the third row we get 32, minus 13 and 58. So one can actually check if this is what you are getting. So we have found out A cube, we also know what is A square. So now we can actually apply these terms in the Cayley-Hamilton theorem and verify if it is correct or not. Is that okay? So the next step is, you have to write what is the, we have to verify CHT. So the actual equation is A cube minus 6A square plus 5A plus 11I should be equal to 0. This is what we have to prove. Okay, so we know the value of A cube, right? So what is minus 6 times A square? Minus 6 times A square is equal to, we have to multiply minus 6 to every single element of the matrix A square. So that way what we get is minus 24, minus 12, minus 6, plus 18, minus 48, plus 84, minus 192, plus 78, minus 348. So this is what we get for minus 6A square. Likewise, 5 times A is equal to, what do you get for that? 5, 5, 5. We are just multiplying every element of the matrix A with the scalar 5. 5, 10, minus 15, 10 minus 5 plus 15. So we all know what is 11i. 11i is actually 11 times I is equal to 1100, 0, 11, 0, 11, 0, 11. Now we can actually add all these things because I have taken negative 6A square here. So we can actually add A cube matrix along with this matrix, along with this matrix, along with this matrix, and check if it is equal to 0. So A cube matrix is going to be, A cube matrix is 8, 7, 1, minus 23 plus 27 minus 69, 32 minus 13 plus 58. Plus, since I have taken minus 6a square, I am actually adding here. Okay, then, so that is going to be equal to minus 24 minus 12 minus 6 plus 18 minus 48 plus 84 minus 192 78 minus 348 plus this matrix, that is 5 5 5 5 10 minus 15 10 minus 5 15 along with 11i 11 0 0 0 11 0 0 0 11. So let us check if it is equal to all zero matrix or a null matrix. So what do we have here? The value is positive 8, positive 5, that is 13, positive 11. So 13 plus 11 is positive 24 and we have negative 24. What I am doing here is I am just adding every single first term of these matrices. Likewise, corresponding second row, first row, second element, first row, second element, first row, second element, first row, second element. That is what we are going to compare. So that way 8 plus 5 is 13 plus 11 is going to be 24 minus 24 will give you 0. So 7 minus 12 is minus 5 plus 5 is going to give you 0. So 1 minus 6 is minus 5, minus 5 plus 5 is going to give you 0. Likewise, if you check every single element, you get all zeros for this matrix. So hence CHT is verified. So first half of the question has been finished. So we have just verified CHT, that is Cayley-Hamilton theorem. That means what? Every square matrix, the given square matrix actually satisfies its own characteristic equation. Okay. So now we have to find out the A inverse. That is our next module. We are going to use this equation that we have just proved, and from that equation we are going to find out what is A inverse. So let me rewrite this equation as to find A inverse, pre-multiply A inverse with A cube 6 minus 6a square plus 5a plus 11i equals 0. If I pre-multiply this with a minus a power inverse, so this is going to be, the bases are same, so the powers we can add. So minus 1 plus 3 will give you plus 2. So this can be written as A inverse of a cube minus 6a square plus 5a plus 11i equals 0. A inverse of 0 is 0, null matrix is 0. So if I multiply this to every term, 1 power of a is going to get reduced. So I get a square minus 6a plus 5 a inverse times a going to be equal to I plus 11 times any matrix multiplied with identity matrix is going to be the same matrix itself. So 11 times A inverse is equal to 0. So we need the value of A inverse alone. So let me take the other values to the other side. So 11 times A inverse is equal to minus A square or minus of A square minus 6A plus 5i. So we need A inverse. So let me take this 11 to the other side. So minus 1 by 11 times A square minus 6A plus 5i. So we know the value of A square. We just have to multiply 6 with the given matrix A and get minus 6A and add that with 5i. That's it. So let me move on to the next slide. A inverse is equal to minus 1 by 11 of A square minus 6A plus 5i. So minus 6A is equal to, so minus 6A is actually actual matrix is 1, 1, 1. So it is going to be minus 6, minus 6, minus 6, and minus 6, minus 12, plus 18. So minus 12 plus 6, and minus 6 into 3 is minus 18. So this is a minus 6A matrix. So if I substitute here, A inverse is equal to minus 1 by lambda. Let me take a curly braces here. So A square value is 4, 2, 1, minus 3, 8, minus 14, 7, minus 3, plus 14. That is your A square matrix. Plus, since we have taken negative 6A here, so we are going to add this. So 6A is equal to minus 6, minus 6, minus 6, minus 6, minus 12, plus 18, minus 12, 6, minus 18. That is minus 6A matrix, plus 5I, that is 5, 0, 0, 0, 5, 0, 0, 0, 5. So this is what is here. So if you add term by term, considering the positive and negative terms, so what you get is 4 minus 6 plus 5. So 4 minus 6 is minus 2, plus 5 is 3. Likewise, if you go term by term, it is going to be 3 minus 4 minus 5 minus 9 plus 1 plus 4 minus 5 plus 3 plus 1. So this is the required A inverse matrix. So the actual procedure for Cayley-Hamilton theorem is very easy. The first thing is we have to just verify Cayley-Hamilton theorem. For that, the first step is to find the characteristic equation, and in that characteristic equation at the place of lambda we have to replace it with the given matrix A, and we have to prove that it is equal to a null matrix or all zero matrix. So after that, using that equation, if they ask for A inverse, we are going to pre-multiply that equation with A inverse, and the identity matrix time A inverse is going to be our important term. So keep that in one side, take the other terms to the other side, we get the value of A inverse. Substitute the required matrices, you will get the actual answer. So this should be easy for you. Please try it at home, and good luck. Thank you so much.